In the previous lecture we were discussing about some exact solutions of the Navier-Stokes equation, and we started with a very simple case of flow through a parallel plate channel. Like this, where if the flow is fully developed and height of the channel is h, and then if you have coordinate system like this, then we derive this expression for the velocity profile. That is where we stopped in the previous class. There might be just an error in writing h in place of h by 2, possibly that was the case. I cannot remember it correctly, but so far as I remember possibly I had mistakenly written this as h, but it is half height, so h by 2, but the form remains the same. Now this is an example where you have the entire domain filled up with one fluid, but if you have an interfacial flow, that means if you have a situation where instead of a single fluid you have two fluids or two phases of the same fluid maybe which have distinct physical appearance, they are separated by an interface. So what kind of governing equations, boundary conditions, etc. we need to use. So that will be the main agenda of discussion in this lecture. So what we will discuss is broadly interfacial flows. So the situation is somewhat like this. You have two fluids, here you have fluid 1, here you have fluid 2, and then this fluid 1 and fluid 2 are separated by an interface which in a functional form can be written as a function of the position vector or the coordinates x, y, z and time t. Now this interface will be expected to dynamically evolve with position and time, and that is why the interface is described as a combined function of position and time. Being a combined function of position and time, any point on the interface, its position, the change in position will be dictated by the total derivative of f, and if it is so that there is a point on the interface which is identified, what we can say from pure kinematic considerations is that a point located on the interface will be located on the interface forever. The interface may dynamically evolve, but it will still be located on the interface, and this is known as kinematic boundary condition. So kinematic boundary condition, so it talks about interfacial kinematics. So this essentially boils down to total derivative of f is equal to 0. So total derivative of f will essentially mean this one, Okay. So, what we can infer from here, so first of all what is this Vs? Vs is a point, velocity of a point located on the interface. What we can say is that this boundary condition will be satisfied irrespective of the form of the interface. A special case when one of the fluids is a solid is replaced by a solid boundary, this kinematic boundary condition will become nothing but a no penetration boundary condition. So, no penetration boundary condition, that is on a flat interface the normal component of velocity at the wall is 0, that is fluid cannot penetrate through a wall, that is a special case of this boundary condition. Now, we have to keep in mind that this Vs is not the velocity of the fluid. When there is no transport of fluid across the interface, then only Vs is equal to V. So, we have a very important question here, that is it equal to V, the velocity of flow. So, if there is no transport of fluid across the interface, then yes, Vs is equal to V. However, if there is a transport of fluid across the interface, then you have to use the relative velocity normal to the direction of interface. So, this is velocity of fluid relative velocity of the surface relative to the fluid, or velocity of fluid relative to the surface. So, this is the difference in normal component of the fluid velocity and velocity at a point on the surface. And how do you calculate this normal direction? So, gradient of f is a vector which is normal to the function f. So, grad f by mod of grad f will give you the normal direction. So, in case there is a flow across the interfaces based on the relative velocity of the fluid with respect to a point on the surface, the normal component of relative velocity, you can find out what is Vs from this equality and then substitute that Vs here in the kinematic boundary condition. So, that becomes a little bit more involved, but for immiscible phases this is equal to V. So, this is kinematic boundary condition, this does not understand what are the forces. However, you also have boundary conditions based on forces. So, first of all we will consider a normal force balance. So, because the interface is of any arbitrary shape, you can write a tangential force and you can have a normal force, and the resultant force is the vector sum of the tangential and the normal component. So, normal force balance means we are considering this eta direction, and tangential force balance means we are considering the s direction. So, normal force balance, what we can say in the so far as the normal force balance goes. So, if the fluid is static, then the pressure difference P1 minus P2 is given by, I am writing a little bit keeping some space, because if it is dynamic we need to add some terms. So, P1 minus P2 is equal to sigma into 1 by R1 plus 1 by R2. This is the Young Laplace equation, which is basically the, what does it tell? So, if you have an interface, I am just making a schematic of a membrane which is a symbolic interface. So, let us say R1 be the radius of curvature of one side and R2 be the radius of curvature. So, these are R2, these are the two centers of curvature. Then the pressure difference across this interface is given by sigma is the surface tension coefficient between the two phases which are separated by the interface into 1 by R1 plus 1 by R2. If it is a flat interface, R1 and R2 are both tending to infinity and then there is no pressure difference. So, pressure difference across an interface due to surface tension can be attributed only to the curvature of the interface. However, this is only under static condition. Now, first point is that where from this comes from a force balance or energetic consideration, work energy consideration. In the course of fluid mechanics, it is beyond the scope to derive this, but normally this is taken up in a basic course of physics. Otherwise, in micro scale flows, because surface tension is very important, this is also covered. If you are interested to understand the derivation of this, please look into my NPTEL lectures on microfluidics where I have derived this. So, now this is under static condition. Under dynamic condition, what will happen? Under dynamic condition, there will be a normal stress beyond the contribution of pressure, and that is the viscous normal stress. So, for that, what we will do is that we will consider the traction vector, deviatoric component of the traction vector, its normal component. Why minus sign? Because pressure by definition is compressive positive and this by definition tensile positive. Interestingly, you can add complicated physics to this boundary condition. For example, the interface is such that there is a thin film of liquid of atomic scale or molecular scale dimension entrapped, or let us say that you have an interface like this and you have a solid boundary and you have a very thin liquid film where intermolecular forces are important. So, in this case, in addition to these forces, you also have an additional pressure which is due to van der Waals forces of interaction, and that is called as disjoining pressure. So, this is a broad way of writing the boundary condition where you can add an additional term. This you can, for this particular course, can simply interpret as molecular component of pressure, that is the molecular contribution, not molecular component, molecular interaction contribution of pressure. So, from this boundary condition, one thing we can clearly assess: if there is no curvature of the interface, if the interface is flat, then this boundary condition does not have any special significance until and unless the molecular effects themselves play a very critical role. However, even if you have a flat interface, the tangential force balance may play a very critical role. So, the next thing that we will learn is tangential force balance. So, let us assume that there is a flat interface. This time we consider the interface like this, of dimension dx. Let us say that this dimension perpendicular to the interface is b. So, let us say that sigma is the surface tension coefficient here. So, the force here is sigma into b and the force here is sigma plus d sigma into b. There is also a shear stress. If there is an interface, there is a fluid at the top, there is a fluid at the bottom. Let us say the difference in shear stress due to the fluids at the top and the bottom, let us say that is tau. Sometimes in proper technical jargon this is called as a jump in shear stress or the difference in shear stress, but you know for all practical purposes we will see that if on one side there is liquid and another side there is air, the shear stress on the air side is negligible. So, this is effectively the shear stress from the other side if it is a liquid air or liquid vapor interface. If there are two liquids on the two sides, you have to very judiciously calculate the difference in shear stress and that is the tau here. So, tau into b into dx. So, if for equilibrium of the interface all these forces are balanced, so that means sigma into b minus plus sigma plus d sigma into b minus tau b dx equal to 0. So, that means tau is equal to d sigma dx. This is true if the interface is flat. This is example of a flat interface. Okay. Now, if the interface is not flat, then we will replace this with something which is the tangential component of the traction vector. In a vector form we can write this. This is the surface gradient, this is called as surface gradient. Okay. So, for those of you who are not really you know I mean so much deeply inclined in rigorous mathematics, still you have to explain this to your students. So, I will tell you, give you a simple trick of how you can give a concept of this to the students without you know getting into the rigor. So, as an example let us think of acceleration as a vector. So, acceleration is the sum of the tangential component and the normal component. Normal component is the this one. In a vector form you have to also give the position vector, unit vector in the direction. So, AS is equal to A minus so AS is helping you to resolve A in the S direction. Similarly, grad S is allowing you to resolve the grad in the S direction. So, grad S will be this grad minus this one. Okay. So, we have now understood the three important boundary conditions to summarize the interfacial flow: kinematic boundary condition, tangential force balance and normal force balance. So, with this little bit of introduction to the boundary conditions for interfacial flows, for the remaining few minutes in this lecture we will discuss about a simple classical problem, very simple classical problem where all these boundary conditions will not be required at all, and that is a thin film flow with a flat interface. So, let us say that there is an inclined plane. In this inclined plane, the angle of inclination is theta. There is a thin liquid film with flat interface. So, this is H. That means that f function of x, y, z time, that becomes a constant H. It does not have any derivative with respect to anything. So, the kinematic boundary condition really becomes redundant here. On this side there is air and on this side there is liquid, and the length of this L is much less than H. The length of L much greater than the length of the incline much greater than H. That means that for all practical purposes the y length scale you may consider to be much less than the x length scale. Okay. So, if the y length scale is much less than the x length scale, then we can make certain conclusions, and one important conclusion, this I leave on you as a homework, that the pressure gradient in the y direction is much less than the pressure gradient in the x direction. Okay. That is true only if this condition holds. If H is of the order of L or even greater, then that does not hold. From common sense you can understand that in that case there will be a pressure difference due to the gravitational the gravity effect. Okay. So, this fact will basically lead to okay. So, thin film flow is a situation where the transverse length scale is much less than the axial length scale. Typically it is a low Reynolds number problem, but the low Reynolds number is not always demanded, but the classical thin film flows are normally low Reynolds number flows. So, this is a normal situation, but I mean you could also have cases of thin film flow where the convective component of acceleration becomes important. So, here we assume that it is a low Reynolds number flow, or to be on a safe side a fully developed flow. If we assume a fully developed flow, then the Reynolds number is not important, because for fully developed flow the acceleration is anyway 0. So, it is an inertia free flow, and therefore it does not matter whether Reynolds number is low or high. So, now let us write the governing equations. So, it is having a translational invariance along the x direction. So, regarding the flow, see you have to explain your students how this is different from the flow between two parallel plates. From the figure it looks like two parallel plates. Of course, here if you have gravity in this direction, you have g sin theta as a component which is driving the flow, but that is not a major difference, because that g sin theta can always be absorbed in the pressure gradient term. So, it will effectively give rise to a pressure gradient where the pressure gradient is triggered by gravity. The major difference is that instead of two rigid plates, here you have one rigid boundary and another interface. So, the boundary condition here is the only thing that predominantly changes, all other factors remain the same. So, Just like the fully developed flow between two parallel plates, you can also write here but there will be an additional body force component along the x direction. This is the x direction. So, body force component is rho g sin theta. Okay. So, now you can write okay. So, what we will do is we will now use a consideration that because it is a fully developed flow, u is a function of x only. So, this is this one. Second, because of thin film flow, the pressure gradient along y is much less than pressure gradient along x. So, this is as good as dp dx. This means that this is a function of x only, this is a function of y only. So, each is a constant. So, okay. So, that means, or in this case you can take this one in the left hand side also, and you can argue because rho g sin theta is anyway a constant, you can treat it as a function of x or a function of y. So, you can also write as mu d2u dy2 minus rho g sin theta is another constant k, right. So, now what is this k? K is dp dx. Because p is a function of x only, this is, say if this section is 1, this section is 2, it is dp dx is p2 minus p1 by the length of the incline, and both p2 and p1 are p atmospheric because it is a thin film moving in an atmosphere. So, that means dp dx is 0, so that means this is 0. So, the film is purely driven by gravity, that is the situation. So, d2u dy2 is equal to 1 by mu rho g sin theta. Okay. So, you can integrate this twice. So, du dy is equal to 1 by mu rho g sin theta into y plus c1, and u is equal to 1 by mu rho g sin theta y square by 2 plus c1y plus c2. What will be the constant c1 and c2? We have to work out two boundary conditions. So, boundary conditions. The first boundary condition is very straightforward. So, at y is equal to 0, that is at the inclined plane, u equal to 0, this is no slip. The second boundary condition is the interfacial boundary condition. Here, because it is a flat interface, we do not require any additional explicit treatment of the kinematic boundary condition, nor we require the normal force balance, because normal force balance is a special equation if the interface has curvature, but we require the tangential force balance. So, tangential force balance, if you recall that it was tau is equal to d sigma dx for a flat interface. How can there be d sigma dx? Let us say you apply a temperature gradient here, you can write d sigma dx is equal to d sigma dt into dt dx. So, if surface tension is a function of temperature, and for most fluid it is, so you can by creating a temperature gradient create a surface tension gradient at the free surface. This gives rise to a fluid flow known as Marangoni convection. In this case there is no temperature gradient along the x direction, that is the description of the problem, and therefore d sigma dx is 0, and therefore we can write that tau is equal to 0. What tau? The difference in tau between the two sides. So at y is equal to h, you have mu du dy at the liquid side is equal to mu du dy at the air side, because mu of air is much less than mu of liquid, and du dy, the velocity gradient in air is also much less than velocity gradient in the liquid. Therefore this is as good as 0. So this is approximately du dy equal to 0 in the liquid, which is our domain. Here you have to give a caution to your students. In most books this is given as a straightforward boundary condition without allowing the students to go through this exercise, and therefore the students in that case do not understand or do not learn the correct boundary condition at the interface. It is essentially a continuity in the shear stress. So when you replace this problem with liquid 1 and liquid 2 instead of liquid and air, students do not understand how to write boundary condition. But when you teach it in this way, instead of air if you have another liquid, students know how to write the boundary condition, then the right hand side will not be negligible. So with these two boundary conditions you can straight away work out the constant C1 and C2. These are straightforward enough in algebra. So I believe that I need not work these details in this lecture. Thank you very much for your attention.